Hello, everyone, and thank you all so much for joining. Today, our speaker is Daniel Hodge, who works under Dr. Richard Sandberg at Brigham Young University. And today, he will be presenting on single-shot X-ray phase contrast imaging of void collapse for fusion energy sciences.
Cool. Yeah, thank you, Kavita, for giving me the chance to give this presentation. I first wanted to start off by thanking SLAC National Accelerator Laboratory, Department of Energy, Fusion Energy Sciences, and the RISE IFE Hub for funding these projects. And if you're interested in this presentation, I'm going to show this again at the end. A bunch of papers that we have done in terms of studying void collapse. And also throughout the presentation, I included like little Dino QR codes. So if you're like curious about the specific papers that I'll be referencing, you could just scan those during the talk or after, whatever you prefer. But first, I wanted to make sure that we were all on the same page. That way, I get no one lost during this talk. So I want to just mention just X-ray imaging, just kind of in general. With X-ray imaging, like the first thing I kind of think of is like going to like the medical doctor, right? Where they take these images, like if you broke your bone, for example, you get images like this, where white is something that's like more dense versus like outside of the area of the bone, you get less dense material. And so this is like the absorption contrast or radiography in the literature. And I also included the super gruesome thing, which is basically like a shotgun accident where someone basically got themselves right in the arm where you can see a bunch of these pellets and of course, broken bone, which is super crazy. But basically, the idea is through absorption contrast, the stark differences between the bone and surrounding material, or bone and pellets in the surrounding material. But the main topic today isn't that, but just to introduce the idea of X-ray imaging, but specifically the manifestation of phase contrast. So whenever I think of phase contrast, I was like a really good analogy or comparison, I think, is the bottom of a swimming pool, right? So everyone, most of us, if not all, have encountered a swimming pool in our life where we could see the bottom of this pool where the surface is disrupted, right, in some sort of way. And basically, the surface of this water is basically acts as like lenses or like these like that basically refract the light, and due to the refraction of the light and the superposition of that and the undiffracted wave creates this structure, this concentration of light at the bottom of the pool. And so if you were to place your hand just underneath the surface, you would get something like radiography, right? You wouldn't see these structures or these fringes. But as you move further down, the distance is what I want to emphasize here is as you increase the distance, you get these structures based on what is projected from the top of the surface of the water to the bottom of the pool. And so real life examples of actual X-ray imaging that basically enforces this idea is this image of polystyrene foam by Peter Clotons. So if we were in this absorption radiography regime for the polystyrene foam, it's really hard to see. But as they increase the propagation distance, or alluding to the previous slide, going further down to the bottom of the pool, going from B to C to D, the structures are much more easier to see. Similarly, with the aluminum-based silicon carbide particle reinforced composite sample here, you can't see any structures if you're using radiography or this absorption contrast technique. But as you increase the propagation distance from the sample to detector, a lot more features are able to be seen. And so the question you might ask is like, when and why is like this applicable, right? So the reason why the bones in the previous example and for the absorption contrast are able to be seen is because of the huge differences in density. Whereas in these particular samples, the differences in density are not as pronounced. And so what you have to do in order to see the edge of these objects is introduce this phase contrast in order to see a lot of these features. And so that is the main focus of our imaging technique that I'll be talking about today is X-ray phase contrast imaging. And so the regimes in which we'll be talking about today, or I guess I'll talk about this in general, is we have this sample that's of size D, and we have plane waves, monochromatic plane waves, interacting with this sample. And there is a so-called direct contrast regime or the near field, right? So radiography would be just right after the sample, the shadow of the object, is what people would say in the literature. But as you propagate just a little further, there's a few fringes in the object. And if you propagate even further to get this holographic regime or this Fresnel region, the edges are more pronounced, as you saw on the previous slide. And if you keep on going further and further and further, you get the full evolution of the sample in which you're imaging. And the particular region in which I'm focusing on today is these two regions here. And the benefit of using this particular imaging configuration is because we can utilize all the photons hitting our sample, and it can be applied to dynamically changing materials of and extended samples as well. But a little change to this is actually what we'll actually be operating is this cone beam geometry, where from a point source, we have this cone beam interacting with our object, which the scattered wave interferes with the undiffracted wave, which gives us our features on our detector. And these fringes basically help us figure out the density information of our sample. And so another important factor I wanted to mention too, because people may not be familiar, is the index of refraction of X-rays, right? So with the index of refraction of X-rays, it's defined as 1 minus delta plus I beta. So delta is related to the phase shifting of the material, beta, the attenuation of our sample, right? So in vacuum, here's just our wave just doing our wave-like thing. But once we introduce this sample, attenuation obviously decreases the amplitude of this wave, but we have a phase shift that's incorporated due to the presence of this object. And there's a phase advance in this particular case because the index of refraction is less than 1, meaning that there's a phase advance in the material due to the material. For visible wavelengths, however, the phase shift would be delayed. So it's the opposite effect for X-rays. And so in particular, we're going to be working with hard X-rays, or at least the experiments that I'll be referencing. And so delta is on the order of 10 to the negative 6, and beta is orders of magnitude smaller, like 10 to the negative 7 or 8. And which basically reemphasizes the fact that if we're using X-ray phase contrast imaging, this is going to be a lot more pronounced because it's orders of magnitude bigger than beta. And so basically, we want to exploit that phase shift, this delta. That way, we can actually obtain reasonable images that we can analyze and get quantitative results from. And so this brings us to exceeding break even, right? So there's a lot of scientific break even that's been done. This is kind of an older slide. I think there's been 8 total. So I have 7 here. So it from 2022 all the way to 2025, there's been a lot of successes in terms of getting a lot more energy output than in. Specifically, earlier this year, we got like a 4 times output, which is really significant. But when I first started, I was like, what does even megajoules even mean? And so I put like an example here, like using your oven for like an hour, it takes like 12 to 28 megajoules, right? So you can cook like taquitos or something, and then that's basically all the energy we basically got out of this interaction. But what we ultimately want is engineering break even, and there's a lot more research to be done because we need this energy output to be significantly higher. And so, in order to do that, I borrowed a slide from a couple months ago from John Klein. I appreciate his emphasis and him showing this slide. There's a lot of factors that can be considered in order to increase the power or energy yield output. But in particular, what I'm focusing on today is basically this 3D compression inefficiencies, this very right-hand side of the equation. Well, technically 3D projected to 2D in my particular case. And so basically what I want to work on is basically this data and modeling, right? So we obtain our data through some experiments and we need to model said data to make sure our results are actually making sense. And so that brings me to the main motivation, right? ICF, which is why I'm giving this talk today to this IFE Hub crew, everyone here. So this top left, I think most people are familiar with here is this direct drive. So there's indirect drive and direct drive for fusion energy. In this particular case, it's direct drive because the lasers are directly hitting this fuel capsule. And inside this fuel capsule is like deuterium or tritium, for example. And in an ideal case where there's high pressure, temperature, and density, uh, it would compress uniformly and get high energy output thermonuclear burn. But we all know that's not the case. It doesn't happen perfectly like that. And the reason why is because of these so-called hydrodynamic instabilities, right? And I think most of us are familiar with space and seeing this Crab Nebula where hydrodynamic instabilities are shown. So like in this Crab Nebula, there's a neutron star that's like spinning. There's charged particles going out, interacting with this supernova ejecta. And because the particles are less dense than this heavier or more dense ejecta, it creates a lot of these nonlinear interactions. And that's why you get these like sort of filament looking structures, these kind of fingers, and which helps like in the formation of stars. And of course, we could see like this is really not uniform due to these hydrodynamic instabilities. Oh, and that's also called like Rayleigh-Taylor instability for further emphasis. But basically, we can also see this on a smaller scale, right? So there was this 3D simulation that Clark made, where basically during this compression, there these instabilities potentially caused by voids in the ablator cause these perturbations to kind of protrude. And you can see on the right half of this, the density distribution is very vast, not ideal. And the left side, red is the speed of the material, where blue is the lower speed and red is the higher speed. And so the main focus here are voids are causing these instabilities, which decrease energy yield. So the question we need to ask here is how do we validate models of implosion in inertial fusion energy? And in order to validate models, we need to basically do experiments, right? And then compare it to hydrodynamic code. And the specific hydrodynamic code in which we work with is X-RAGE, which has been developed by Los Alamos National Labs. But first, before I dive into all of that, we do our imaging at the Linux coherent light source. So at the Linux coherent light source, it's basically this 2 kilometer structure of basically electrons being accelerated at relativistic speeds. And these electrons are generated by this UV light, essentially ejecting electrons from a metal. This linear accelerator accelerates the electrons, and these electrons, they encounter this undulator or these series of magnets, and by interaction with this magnetic structure, these electrons oscillate or accelerate. And because electrons are accelerated, they emit radiation. And due to that radiation, they over time become coherent and can be used at where we were taking our data at this far experimental hall. And the reason why we use this huge structure is because it's a very coherent source and it's extremely bright source to punch through very dense plasmas. And to emphasize that fact further, here's a comparison between like a free electron laser and a synchrotron, right? So at an X-ray free electron laser, we have 10 to the 13 photons versus orders of magnitude lower synchrotrons where you don't get as many photons. So we need all the photons we can get so we can actually see the material and plasma that's generated from the compression of our sample. And so that brings us to the experimental geometries. So basically, how I'm going to go about the rest of this talk is basically it's going to be like a lessons learned as time went on. So the very first experiment wasn't like the greatest, but once we get to the very last experiment, we're able to get a lot better quantitative information out from our experimental data. And so the first experimental geometry. And a really unique thing, I think, with LCLS, I'm not sure if other free electron lasers have adapted this, because it's been a couple years, but maybe they have, is that the LCLS is capable of sending in 8 pulses uh, that can interact with your sample. That can be separated by a couple of nanoseconds between each pulse to interact with our sample. Um, But in this particular geometry, uh, in this first experimental campaign that we did, we used this so-called Icarus V2 camera. This camera is an ultra-fast X-ray imaging camera, meaning that with a single sample, we can capture 4 frames of that sample as a shock wave interacts with this sample. So between each of these frames is 2 nanoseconds. So we could see the evolution of the shock wave as uh, as it propagates through. And basically, how this camera works is there's basically this transistor, which is an electronic shutter, and it basically controls the integration time of this ultra-fast X-ray imaging camera. And uh, and in order to even get these four frames, each pixel on this camera has basically four capacitors that can basically take in charge and then it's read off at a later time. So that enables nanosecond recording of images when this compressive wave passes through. And so, yeah, we also have this beryllium compound refractive lenses that are used to focus the sample to then, sorry, focus the X-rays to then have this cone beam on the sample to then magnify the image. And of course, yeah, these are the undulator, the magnetic structure as well for uh, generating the coherent beam. Oh, another thing I should mention too is we are in this holographic regime, so I'm calling back to that slide with the different regimes. This dx squared is the effective pixel size accounting for magnification. The z is the sample to the detector distance. Lambda is the wavelength of the X-ray free electron laser. And if that's much less than one, we're basically in this regime. And another experimental geometry is the only thing that's difference between here and here is the fact that the compound refractive lenses is now after the sample. So what this can be viewed as is basically a very expensive X-ray microscope, right? So there is a little bit of defocus. We're closer to, so there's less fringes and not as far propagated. And we're in this regime based on this definition here. So the trade-off between these two geometries is, or not the trade-off, but with using the ultra-fast X-ray imaging camera, the trade-off is there's a 25 micron pixel size, so the resolution is a lot worse. So two of the four campaigns, we use this geometry, but in the other two geometries, the other two campaigns, we only used a single frame camera, the Xyla, which gives us better resolution because it has a smaller pixel size. And so, oh, yeah, to reemphasize again, the Linux coherent light source, it basically works through self-amplified spontaneous emission. So basically, these accelerated electrons, they oscillate through this undulator, uh, and they're bunched up like this initially, which is depicted in this bottom left picture. And as time and distance passes, as it goes through this undulator, they start micro bunching. And this micro bunching is about a wavelength and distance here. And eventually, after some distance, these electrons start bunching up, like I mentioned, and they emit coherent bright radiation. And so, yeah, so going back to the geometries, these are the samples in which we use for the shock wave void collapse. So what we're seeing here is SU8, or basically like this epoxy. And within this epoxy is this hollow glass void. So that is representative of our voids in the material. And this void is around 40 microns in diameter. And the thickness, if like were the X-rays passing through it, the thickness of all of this is 400 microns all the way through this SU8 or epoxy. And the reason why we use these materials is because it has similar shock properties in response to ablators that are used in current ICF experiments. And so to have sort of like an apples to apples comparison, we used materials that have similar response in that sense. And the reason why we made our samples this way is very convenient. So this epoxy is basically put on the substrate, which can be spun to make it like super homogeneous. And then you could spin it to like you could have this to some height or some thickness, and then you can place this hollow glass void. And then you can put the epoxy on top of that to basically have this void in the center of the material, and then spin it again to make it a very homogeneous sample. Because the only thing that we want varying, or the only thing we truly want to study, is the void shockwave interaction, and not have other things be inhomogeneous. So we need that uniform thickness of our sample so we can get accurate representation of the void shockwave interactions. And so that brings us to the first experiment, right? Where in this Fresnel regime where it's greater than or equal to 1. Uh, so we're in this regime here. So here's our static sample, 40 micron diameter void. Here's the sample boundary and the remainder of the X-rays. There's no sample. Here we have a main shock and a pre-pulse. Pre-pulse was an issue. This is using the ultra-fast X-ray imaging camera, just to emphasize again. And then a couple nanoseconds later, this shockwave evolves, interacts with our void even further, and and then we get another interaction of our shockwave with this void. So even though 4 pulses are sent out to, we should actually have like 4 dynamic frames. We actually lost a frame because of the low signal to noise, and uh, so that was a consistent theme. So we're able to only capture 3 dynamic series in this particular case. So 2 nanoseconds later, and then another 4 nanoseconds later, where we lost the third frame. So one thing I wanted to point out though is that in this geometry, because the density is so high in this particular region, refraction is like really, really significant. And because it's so significant, it creates this dark band where we really can't really see anything. And we actually want to see something in this dark band or dark region because that's information as the shockwave encounters the void. There's going to be some break off or some other nonlinear things that are happening that we need to know. So that was like one mistake of being in this particular geometry is that we weren't able to see a lot of these features. And that's because we were operating at too low of an energy. And so, uh, still on the first experiment, simulations were made, basically showing why refraction was the issue, right? So if we have this mock shockwave that's of a particular radius with our like a 10 micron sized void at 8 keV, that's obscuring a lot of the information. But if we increase the energy to, for example, 16 keV, we could see a lot more of the void, and correspondingly at 24 keV, we could see a lot more of the void. So the issue is that we were at too low of an energy, which I guess is an emphasis that it's better or good to model the experiment, or at least close to the experiment as much as possible. So lesson learned. And so there's a lot of factors that affect our ability to image. And so we had a
There's
second
a
experiment.
question,
Oh,
Daniel.
sure.
Oh,
Yes. Yes, yes, yes.
go ahead, Nick.
Hi, hi Daniel. Yeah, I see the point about the simulation. I was curious, when you do those different simulations, does that account for the fact that you get far fewer photons at 24 keV, or does that not really matter?
Yeah, so yeah, these are just like just basic mock simulations just to see just the effect of the shockwave.
Okay, so
Uh
there's no like signal to noise or no sort of expectation of, because obviously you would get a lot fewer photons if you get such a high energy, right?
yeah, but as I'll show like a lot later, it doesn't really matter. Like it doesn't
Okay.
affect us. The point that I was trying to drive home here is that we want to be able to see the features and we need to go higher energy essentially. Um, But another way to go around this is by operating in this near field. So instead of being in this regime, we should be in this regime. So not necessarily radiography or absorption contrast, but more so in this near field regime. And in this particular case, we could see this static image of the void, and we could see a lot of the nonlinear features with the void shockwave interaction, and we could see that the void kind of shrunk in size in a little bit, but also shifted linearly from its original position. And we could see that the shockwave here is basically already past the void, and there's a lot of nonlinear features due to that interaction in this particular geometry. And at this point, we're at a pretty similar energy from the last one, 9 keV, right? So we are at a similar energy, but because we didn't introduce as much phase contrast, or the refraction doesn't take as much as an effect, we can actually see a lot of features. And this is a lot less grainy because we were using this Xyla camera with a 6.5 micron pixel size, so we have better resolutions. There's a trade-off with resolution here. Like you can get multiple frames at lower resolution, or you can get a single frame at better resolution. And so we had a third experiment where we operated again in this regime, but except we used the ultra-fast X-ray imaging camera. So effectively, by moving in this regime, or by switching the beryllium compound refractive lenses with the sample position, just flipping those, it effectively reduces the amount of phase contrast or that sample to detector distance, like I mentioned, which is why we're able to see a lot of these features significantly better. But with the UXI, lower resolution. But here's the static sample, and these lines here are the aluminum and Kapton layers before this void to enforce uniform shock propagation. And then this feature here, these are like lens defects, and all this other speckle is basically the dust on the lenses. Because the X-ray beam is propagating through a lot of optical elements, and so there's going to be a lot of features that are in our sample. Then the shock wave is sent through, interacts with our void at 4.6 nanoseconds, and then a couple nanoseconds later, it progresses further through the void, where it's shown right here, and then finally it progresses all the way through the void. And as you can see, the second frame is significantly better, and there's actually stuff behind the void in comparison to what was happening in this previous image here. But the trade-off, again, I'd really want to emphasize is working with larger pixel sizes. And we would also like to have a better magnification because we're kind of really zoomed out. We want to be able to zoom in to see features at a higher resolution. And so that brings us to this comparison of the first and third experiment, the holographic versus the direct contrast regime. Um, just showing that this regime is better for very dense interactions in the material. And so, I mentioned a lot earlier at the very beginning that we compare our intensity images to X-range or this hydrodynamic code. From this hydrodynamic code basically generates like these density maps, and also what you can create from this code is these Fresnel propagated phase maps, and from these or intensity maps. And so we can compare one frame of this experimental image where this shockwave is interacting first with the void, and we can compare it to what X-ray is producing at this particular time frame. And then we have a couple nanoseconds later, this interaction, which we can compare later on in the X-ray simulation, this interaction. And so the benefit of having X-ray and why we want to improve X-ray by getting experimental data is because X-ray has a higher temporal resolution. So if we can make X-ray more accurate by tuning parameters, we can see the evolution in between these frames, which is shown in D. And I thought it was a little fun thing here, like this interaction here kind of looks like a dropper popper. I didn't know the name of this thing, but I think maybe some of us play with this as like kids or something. But it kind of looks like that, where the shockwave accelerates in the void faster than the shockwave outside the void. And so this leads us, so with this gives us basically these density maps. From the intensity images, we can get these intensity maps, these density maps. And the first thing you'll see is like, oh, what the heck? Why is the Kapton illuminator so high in density? And why is there even negative density? So I really wanted to emphasize the fact here that this is at the time, this is very preliminary results. And due to the noise, the low signal to noise in some regions, and this assuming that it was a single material sample, which is not necessarily true because it was two materials, this hollow shell and this SU8 epoxy. So that's why we get this sort of weird range scale. But the idea is to like see roughly the evolution of the density as this shock wave propagates through. So this brings us to the fourth and final experiment, the single shot imaging with the Xyla camera. So this basically combines everything that we have essentially learned, right? So what we want is high resolution. So we chose to do the Xyla camera. We wanted to do this particular geometry using X-ray phase contrast imaging in this Fresnel region because we wanted to magnify the sample to really zoom in on this sample, especially when the shockwave is interacting with the void. And to avoid uh, that dark band so we can actually see information before the shock front, we operated a much higher energy, so 18 keV X-rays. And so in this particular setup, it's the same as before, except we just have one single image, a long pulse laser at the matter in extreme conditions instrument smacks our sample at the same time these X-rays pass through, and we get our image out. And so what we want ultimately is the areal density, but there's a lot of factors that we need to consider. A lot of pre-processing, which very heavily contributes to uh, the quality of the phase retrieval or getting the areal density information. So one of the challenges is we have to deal with the X-ray free electron laser noise. It's stochastic. As you can see here, these are the so-called white fields or flat fields in the literature. So this is basically just the beam with just the sample out. So there's a lot of lens features and dust that's on the lenses, and there's a lot of beam fluctuations, and that's because of the number of electrons in these micro bunches that I mentioned. The bunch spread because they're not perfectly like confined, and it's all due to this self-amplified spontaneous emission process. So there's a lot of lens artifacts, detector noise, shot noise, and that just ultimately really destroys reconstructions or getting quantitative information. Another issue, especially, is we only get a single image out, right? Because when the shockwave interacts with the sample, it destroys it and it's gone. That's it. Unless you're using the ultra-fast X-ray imaging camera where you can get multiple images out. But having only a single image or a single frame, even with the UXI, because each frame is different, it's going to be harder to constrain the problem. Because normally, how people constrain the problem is like putting your object at several distances, but we can't do that because our sample is destroyed at a very short time frame. So we only have one image to work with. Another issue is a circular field of view. So we lose all these diffraction fringes that are outside this region. Um, and that's because of this compound refractive lens. There's like this aperture at the end here that's basically excluding all of this extra information that would help with the phase retrieval or obtaining the areal density. And another issue that was a problem for a very long time, and I didn't realize it, is that there are fringes here which correspond to information, like it corresponds to the aperture of the CRL, uh, which need to be removed for accurate uh, reconstructions because we don't want to reconstruct the compound refractive lenses due to these fringes, but the actual object itself. Another issue here is that we have to deal with a multi-material. So we can't truly enforce single material constraints with high accuracy, which is an issue. So that's another thing. Another thing too is large phase excursions or these large phase gradients, right? This compressive wave is compressing a material significantly such that the shock wave is really strong phase gradients compared to the rest of the material. And so you have to do something like phase unwrapping, but you get like these artifacts because phase unwrapping could introduce these artifacts in this, and also phase unwrapping leads to a lot of computational speed issues. Another thing you have to consider too is this point spread function blur, right? Usually if you have a point source and then you have like it expands out, hits a lens, ideally it would go back to a point source. But because of imperfect optics and the partial coherence of the X-rays, it's going to cause the final image to actually be blurred. And you have to perform a deconvolution to reach the attainment of larger phase excursions or these phase gradients in the reconstructions. And there's another issue that with this given field of view, we're in this near field regime. We're in the combination of this direct and holographic regime based on the size of features of our sample. And the last issue that we have to encounter or fix is the dilation due to it's not fully monochromatic, the X-ray free electron laser. And so because it's not fully monochromatic, the focus deviates, causing this dilation of our sample intensity image. And so in order to get quantitative information or do phase retrieval, we first have to do some pre-processing. So here are some images, raw images of our data, 40 micron void. The whole field of view is like around 60-ish microns in size of our static and dynamic sample. What you're seeing here in the dynamic sample is here's the main shock wave where it's really bright, and then here's secondary shock waves that are occurring due to the interaction with the void. So the first thing we need to do, or that I considered to make these images as clean as possible, is this so-called principal component analysis. So basically the idea of principal component analysis is that it takes in all of these white fields, right? There's so much deviation, there's so much noise, intensity variations, and you throw it into this algorithm. And basically this algorithm basically finds the highest variance in that data set. And in that data set, the highest variance, for example, is the intensity fluctuations. That's the thing that's varying the most. The second most, for example, would be the pointing stability of the beam, or the center of the mass of the beam is shifting up, down, left, right, so on and so forth. So there's a lot of things that are contributing to all of these white fields. And so what PCA produces are these components. These components basically explain the underlying structure of our white fields. And basically what it does is create this ultimate white field, which we can divide our object images by, right? So we can get a nice clean looking image, right? Except we see that there are these high frequency features that are still present in the image. And these high frequency features are because of these defects on the compound refractive lenses that are focusing down our X-rays. And even more importantly, with the dynamic image, the refraction is so strong that relative to the white fields in this region, the white fields, when they're divided out, or this synthetic white field that's divided out, it misses a lot of these features. And so it's really horrible in this particular region. So what we do, another method is called image registration or image alignment, which basically takes every single pixel in the white field and warps it to these static and dynamic images. And if you do that, it does a really, really good job of eliminating these high frequency features. But the downside of using this particular method is it's darker in this region and white and lighter in this region. So if I were to get some reconstructions going on this particular object or this intensity image, it would interpret that this is more dense here than this part of the image. And that's an issue because we know this is supposed to be mostly uniform as we go up, down, and left and right. So what we do is we do the combination of both, right? So we use our principal component analysis to get basically our ultimate white field, and then use image registration to basically align that further, which basically makes a very good flat field corrected image, which removes those imperfect features. And we could see it's a lot more uniform than what it was before. And this is used as input into the algorithms. And so what we need to do now, so if we want to get really accurate quantitative information, we need to do some forward modeling, right? So we need to forward model our white fields, just the beam on the camera. And so with this beam on the camera, so we have our Gaussian, right? And with this Gaussian, it's going to be shifting left and right. The amplitude's going to be changing. And then we also need to model the speckle. The speckle is basically a 3D box with ellipsoids that we project to 2D. And then it produces C, this exit surface wave, which then it propagates all the way to the detector and we get our simulated white fields, which closely corresponds to what we see for our experimental white fields. Similarly, we need to do our static and dynamic X-ray phase contrast image of our forward model. So we still have our Gaussian beam hitting so this is all in a single plane with our speckle that's on the lenses. And then we need to introduce our object itself with the speckle as denoted in D. And then E, we have our exit surface wave, or just the complex amplitude and phase right after our object. That gets propagated to the detector, and we get our simulated static image. And then we could compare that to our experimental one, and we could see that they closely correspond. And I should also mention that in this model, we include Poisson noise, the point spread function, and yeah, and the point spread function to kind of replicate the blur that we're seeing experimentally. And so if we apply the phase, sorry, we apply the flat field correction technique for phase retrieval, uh, like I showed a couple slides ago, we get this output. Um, which are flat field corrected images. But as you may notice at this bottom portion of this void here, it's in like it didn't really correct for that. And the reason for that is because we took our white fields at a later time, which the white field should be captured either right before or after data acquisition. Otherwise, it's not going to properly align. And similarly, uh, with X-Rage, we can, using simulations from X-Rage, we can forward propagate those results from X-Rage to get a similar dynamic image that's simulated, and also compare that to the experiment here, perform our flat field correction as we see in B and D that corresponds to those images. And so now I really want to emphasize the importance of phase. So if we take this cameraman and these vegetables and we take like the Fourier transform of them and we keep the magnitude the same, but we swap like the phases of our object, then and then we perform an inverse Fourier transform, we can see that the phase contains the majority of the information, which is why we do this phase retrieval, because it contains all this information. And so this is just to emphasize that fact. And so in order to get this density information, or correspondingly the phase, I keep saying those interchangeably, but basically they're the same. Is if we have like our intensity image on the detector, iterative phase retrieval algorithms work this way. We take the square root of this intensity pattern. We could seed it with the phase with either 0, or have it be randomly seeded, or even better, have a really good guess on what this phase should be. And then we could back propagate that to the object plane, where we can enforce some constraints, right? So we could say like, oh, maybe this object's in a particular region, so you can mask the object. Or you can say, oh, the bounds of my object should be between this value and this value. So those are some common constraints that people can do for phase retrieval. And then once you updated this so-called transmission function T, that's the amplitude and phase of your object, you can then forward propagate that to the detector to get an intensity pattern that, after many iterations, should look close to what you measured, right? And so then you implement this Fourier constraint to then get this updated diffraction pattern. And you just follow this process over and over and over again to get this final result of this hollow shell inside this SU8 material. So what you're seeing here is this hollow shell, and the black is the shell itself, and then outside's the SU8. Black, in this sense, is more dense, the lighter is less dense. And the reason why we want to do this is to obtain the density, of course, to better model instabilities in hydrodynamic codes. And so that brings us to the projected electron density and areal density and how we derive that. So the index of refraction, like I mentioned before, 1 minus delta plus I beta. We can define the phase as the wave number times the integral of this phase shifting, that this delta that governs the phase shift. And this delta can be defined from this paper by Indrizzi. It can be plugged into this. And from that, we can get the projected electron density sigma. And from this projected electron density, if we assume a single material, or if at least it's close to a single material, we can get the areal density out, which is grams per centimeter squared, versus mass density, which is grams per cubic centimeter. And of course, density for the quality of compression and to better model hydrodynamic instabilities. And so I used two algorithms to get phase retrieval results. I think I'm coming close on time here, so I'll try to go through this really, really fast. So I need you all to believe me that through the Fresnel diffraction formula, and assuming uh, that either our phase is slowly varying and or our phase is slowly varying, and that our phase is either small or mu is really small, we can linearize the transmission function of our object. And we can express this equation here. So we can get this contrast transfer function, um, which is basically this deterministic phase retrieval algorithm, which essentially is like you throw in your intensity pattern and it spits out a phase retrieval result. Um, so it's not iterative. You just throw something in, it spits something out. And we add this frequency dependent regularization because there are zeros in this denominator here in this contrast transfer function for the phase. But also, I couple that with an iterative algorithm called projected gradient descent. And this is particularly useful because it works directly with the refractive index, this particular algorithm. And basically, if you were to just do phase retrieval like normal, if you have something that's super dense, you have a very large phase range. It gets trapped, like you see in B, it gets trapped in this negative pi to pi because it's e to the I phi. But if you were to do some phase unwrapping, which is computationally expensive, it still kind of fails reconstructing the interior of this magnesium wire object. But with their particular algorithm, they can reconstruct the interior of their object very successfully. And uh, and you can avoid unwrapping altogether. And so to compare with X-ray simulations, this is the ground truth top left, our intensity images that we flat field correct. And using the CTF method, the first deterministic method that I mentioned, we can get a really good phase guess that we can then put and seed into this PGD reconstruction. The CTF is really good at reconstructing the slowly varying phase, whereas the iterative methods are generally good at reconstructing sharp features. So throwing that into this algorithm for the simulation on the top and experimental on the bottom, we get pretty close results. And we can also do corresponding lineouts, which shows that for the static case, it's fairly accurate, and there might be some deviations due to improper or not perfect flat field correction. But the results are fairly close in terms of the output. And similarly, from X-ray, we get the dynamic case, and then we could do our flat field correction, apply our contrast transfer function to get really good guesses of the dynamic compression, and then we can apply the PGD reconstruction. And if we do lineouts with that as well, we can see that we get fairly close results between simulation and experimental. And just to note, I also used like the same parameters to get this line to the experimental. That way, there is no like qualms or questions on how I got this reconstruction relative to the simulation. But to kind of close up, uh, we basically have a couple ways to check simulation fidelity. One through phase reconstructions that I just showed, but another through just comparing the intensity patterns themselves. So this very right image, the left is produced by X-ray, where the right is the experimental. So there's a lot of similar features, but a lot of features that are not super similar. And there's a lot of interactions that are important in this void collapse process that I don't have time to really go through. Um, but the idea is that we use this X-ray phase contrast imaging because we have materials of similar densities, and we want to utilize all of these photons to image the material. And pre-processing and the is super vital for getting phase retrieval results that are actually accurate. Um, but in the future, what we want to do is work on this so-called time series, which of this void compression going through the sample. So that is future work, but that's everything that I have. I just want to thank everybody for listening and all these people for helping out with these projects. And hopefully I was clear. So thank you, everybody.
Let's thank our speaker.
Hmm.
Are there any questions from anyone? Feel free to unmute yourself, drop them in the chat. So, okay,
Hi
go
there.
ahead, Nick.
Thanks. Sorry. Thanks for the great talk. I have another question. You talked about the shot coming into the void and then reflecting, and that's why you had those sort of lines above it.
Oh, yeah.
I mean,
Let's
I
see.
imagine if they're reflected, they wouldn't be parallel, right? I imagine these are shocks coming in from your ablator rather than something that's causing from the
Oh,
interaction.
I might have misspoke. Let's see where that's. Oh, here,
I mean,
right?
yeah, those ones
No, these are
exactly.
the secondary shocks, not the reflected.
Okay, sorry. I
So
thought you said something about from the interaction with the void. Is that not true?
there might be some interactions that
Okay.
from the void that might be affecting this area. I guess that's the reason why we ultimately want to compare. Um,
To a void model.
yeah,
Yeah.
we want to compare like what we're seeing like with this like this that image that I show is different. This is a
Hmm.
different void collapse image, but that's why we want to do this comparison because like what's actually happening in that experimental reconstruction because yeah, because those two lines do appear in the simulation, but not that far apart. So there's like some
Okay.
deviations, and that's why we're
Is it
comparing the
just
two.
from the ablator? Is it just like reflecting shot coming in multiple times? And if the ablator thickness is a bit different, you're going to get those differently spaced?
Yeah, I think because of there's a Kapton and aluminum layer, so when the shockwave
Yeah.
goes through, I
So there's a
think
load of things
those
that could get
secondary shocks, it's
reverberations.
bouncing off of something from before and coming down.
Gotcha. Thanks.
Yeah.
Go ahead, John one. If we can't hear you.
Can you hear me now?
Yep.
Okay. My question is about the when you mentioned like you changing the energy of the X-ray and that minimize the dark fringe. Is that because of the wavelength difference and the coherent superposition of the light that makes the some of the regions dark?
So you're asking,
I'm asking the previous one you mentioned, you said this big dark region that almost like covers all the information.
oh yes, okay. Yeah, the dark band.
Yeah.
Yeah, so yeah, from what we deduced, yeah, lower energy, it doesn't punch through this particular dark band or because of strong refraction effects. But yes, increasing the energy of the beam allows us to actually see these features now, um, which is shown here. This is a different sample of the phase retrieval that I did, but basically this is the 18 kV void shockwave interaction uh, in this similar regime where now it's not obscured anymore.
Thank you.
Yeah.
And Daniel, I think it's not that that's more absorbing. If I'm correct, I think it's that there's less refraction
Oh yeah,
because
yeah, yeah, yeah.
when
It's
you
the
have the
refraction effects. Mhm.
right, yeah, because when you have the what we call the money shot, right, you can punch right through it, so it's not an absorption effect.
Oh yeah, yeah, because yeah, this thing. It's not an absorption issue, it's a refraction issue.
Hmm. So the shock wave front is just like an edge propagating forward, and the fringes I mean the multi fringes you see is just the edge effect, the X-ray scattering off that edge and form these fine structures in the in your diffraction pattern, right?
In these particular ones?
Uh, in your retrieved features.
Um, Further, here we go.
That yeah,
Like here?
yeah, like in the intensity image, along the edge, there are these fringes.
Oh, yes, I didn't have time to talk
Yeah,
about that.
yeah.
So an important part of phase retrieval here that was a huge problem is the fact that it can't be zeros out here on this exterior region. So in order to help it converge to the right solution, and also to exterminate the fringes due to the CRLs, you have to extend this edge and smooth out, and I smoothed it out radially to the average value of that edge. And then that was put into the phase retrieval algorithm.
I mean, these fringes are very common in optics when you see, especially when there's light uh, diffraction off a like a blade. These are very common. So explain and also explained in optics books, like almost everyone. Yeah. So maybe you look up that, then you, yeah, then you don't need to average out. Maybe you would be able to retrieve even sharper edge.
I see.
Mhm.
Can I comment and ask a question?
Sure.
Yeah, great talk and very exciting work. Here at Texas A&M, we have a project unrelated to the laser-driven fusion activities, but still, it's inline holography that we use for detection and identification of microparticles. So it's an optical analog of what you're doing in X-ray, I believe.
Mhm.
We use visible light and shine it on microparticles and look at these holograms, inline holography. And what we find useful is artificial intelligence of neural networks type. We use AI to help in retrieving the images or identifying particles or identifying what's happening without necessarily retrieving the images. So I wonder if you have considered using AI for image processing here.
For the image processing, no. But for the phase retrieval, I I have tried unsupervised machine learning techniques, which did not turn out to do super well. Um, Also, it would be really hard to do like training for like if I were to do like a supervised machine learning because X-Rage takes like a really long time to run for even just a single sample. And
Mm.
so the lack of training data would make it really hard for us to use uh, this AI kind of stuff. So I have dived into that like a little bit. It just seems not ideal to use in my particular circumstance. But maybe there's some alternative way that I'm not aware of. I'm totally open to it because I think it would be interesting to use.
Okay, thank you.
Yeah.
Thank you, everyone. Are there any final questions from anyone? Well, with that, I'd like to thank Daniel again for such an excellent talk. I learned a lot, and I hope others have as well. And looking forward to seeing everyone next month.